Hello. This presentation corresponds to the first part of the third PowerPoint in the Neural Network series of Dr. Haziaskar. Recall that in part 1 we talked about neural network model representation, setting up the idea of neural network, talking about layers and neurons and activation functions. In part 2 we talked about neural network learning, including backpropagation, which enables us to improve the neural network weights to have it perform better at the task that you want it to do. In part 3 we'll talk about neural network design. In other words, how to arrange your neural network in order to accomplish the task you want it to do, whether it be regression or classification. So the discussion of neural network design will be divided into two parts: a new way of looking at neural networks, and then that will set the stage for our discussion of designing neural networks. So let's continue. Right? So think of a neural network as some kind of machine that you provide the components and you connect them loosely. In a way, this is like collecting tools for a toolbox, but it's a little bit more than that, because you are deciding some connections between the components that you are using. And this corresponds to what are called hyperparameters, which are decisions you make about the neural network before you try to optimize it. All right, now, then backpropagation comes in and takes your rough design and uses information about the inputs the machine should take and the outputs, and configures the connections between the components. In other words, backpropagation says, okay, you've given me this structure, and you want this structure to produce these outputs from these inputs. So we're going to optimize or tune your structure to enable it to produce the desired outputs from the inputs that you give it. Now, backpropagation is not a miracle worker. It can only do the best with what you give it. So you have to decide the components. You have to decide how sophisticated the machine should be. So if the components are too few or too simple, the backpropagation will produce a simple machine which may not be adequate for your task. And of course, your inputs have to relate to the output. We say garbage in, garbage out. The only thing that neural networks can do is extract information. They cannot create information. If the inputs really have nothing to do with the output, then trying to use a neural network for prediction or classification of the output is useless. So, as mentioned previously, the more hidden layers we provide, the more sophisticated complex features backpropagation can try to produce from the input. So the number of hidden layers matters. The more hidden nodes we provide in each layer, the more different variations of complex features that backpropagation can try to produce in that layer at that complexity. So in other words, both the number of hidden layers and the number of nodes in the hidden layers contributes to the possible complexity of the features that backpropagation produces. Now, providing nonlinear activation functions on hidden nodes makes it possible to create complex nonlinear functions. If you don't have the activation function, then no matter how many layers or how many nodes you have in your neural network, you are just creating a linear function. And in fact, the number of layers and number of nodes will not do anything to improve your performance. they'll just sort of collapse together and won't affect the output at all. So the nonlinear activation functions are the key. You need those in there. So using and starting with the rough initial neural network machine we created with loosely connected components, Backprop is all about continuously doing the following. Passing the inputs through the machine to get outputs. So this is forward propagation. Using a loss function to compare the outputs with the required output to see how well the machine currently does its job. Then using gradient descent to go back and make changes to match the outputs with the inputs. Now these are all aspects that we have discussed in previous videos and are also contained in the first two PowerPoint presentations. Now here's a familiar picture of a neural network with two layers, and you see the connections, the weight matrices theta 1 and theta 2. And we can trace through how the inputs affect the outputs, right? The inputs from the first layer create two outputs, Z1 and Z2, which are going to become A1 and A2. Now suppose we don't have a nonlinear activation function and we simply set A12 to be equal to Z12. So we'll similarly get A22, the Z22, as a linear combination of the inputs. And then we'll go to Z13, which gives us the combination of the A's. And we can trace this back by plugging in the A's, right? This Z13 depends on A12, which I get from here, so I can plug in these theta, these thetas from the first layer with superscript 1 in for A12, and also these thetas from the first layer into A22. And I get this expression for A13 as a linear combination of linear combinations. And I can rearrange by distributing these multiplications. And then finally, I get A13 as a linear combination of x0, x1, and x2. So you see here that all these weights, if there's no nonlinear activation function, all these late weights sort of collapse, and I simply get a single weight for x0, x1, and x2. However, if you have the nonlinear activation functions, then this collapse is not possible. Because, for instance, here I would have a phi, my nonlinear activation function, and I couldn't distribute. So this illustrates the point that the key role of nonlinear activation functions that distinguishes neural networks from, say, ordinary linear regression or logistic regression. Okay, we'll stop here, and then in the next video we'll talk about issues involved in designing neural networks. Thanks for watching.